Okay, so first of all, my name is Belen Bermejo. I'm from the University of the Balearic Islands, and I would like to start say thank you to the committee for the opportunity of being here today. And during this short time, I'm gonna present the overview of my PhD thesis, which is called Performance and Energy Consumption Trade-off in Server Consolidation. So let's start with the scope of this thesis. As all we know, the increase in IT energy consumption is continuously growing day by day. A huge part of this energy consumption comes from the data centers, which are responsible for almost half of this IT energy consumption. At the same time, from these data centers, the servers, the physical servers, consume a half of this data center's power. Some years ago, in order to mitigate the effect of this energy and power consumption, the Green IT appears as a set of techniques and good practice in order to improve the energy efficiency of these servers and data centers. One of these techniques is the server consolidation, which is based basically in the reduction of the power consumption by allocating or grouping the maximum workload in the minimum number of the physical servers. So consolidating servers, we can reduce the power consumption of these servers, but on the other side, the percentage of utilization of the resources of these servers we are consolidating increase. So on the one hand, we have a reduction on the power consumption and a saving in the energy, but on the other side, we have an increment of this percentage of utilization, which implies a performance degradation. So we have a trade-off between on the performance degradation and the energy consumption. So we need to find a balance between the energy savings and the performance degradation when we are consolidating servers. On the state of the art, there is no way to manage or to quantify this trade-off. So in this thesis, mainly, we propose the FIS index, which is a metric in order to measure and quantify the performance and energy trade-off when we are consolidating servers. And as a second contribution, we have the study of the consolidation overhead, which is provoked by this performance degradation. So let's go in depth to the server consolidation. In this picture here, we can see three physical servers, the physical server A, B, and C, and we have a set of virtual machines we are allocated among these physical servers. So we can move the virtual machine from the server A to the server B, and the virtual machine to the physical server C to the physical server B. So we are incrementing the utilization of the physical server B because we have more virtual machines in the same physical server. So we have an inherent performance degradation due to this migration. On the other side, if we are not using the physical server A and the physical server C, we can switch off these two physical servers and we have a power saving in this way. In this case, the energy savings depends on the performance on the server B. But in any case, we can see that the consolidation of servers is not for free. So on the one hand, we have the performance of the physical servers we are consolidating. And on the other hand, we have the energy consumption or the potential energy saving of these physical servers. And in the middle, we have to manage this trade-off between this performance degradation and this energy consumption. But in this thesis, we are considering the server consolidation. That is, we are considering how many virtual machines or how many containers I have consolidated in this physical server. So we can apply all of this result in this thesis in any consolidated server or any virtualized servers and data centers. So in order to face this research challenge, we can define 5 statements or 5 research questions. The first one is that there is no metric to express the performance and energy trade-off when we are consolidating servers. Then we have to study how the performance degradation can be traded off against this energy consumption in order to find the most suitable balance between these 2 variables. The third one is about the server comparison, how we can compare different servers in order to find the best consolidation for a specific scenario. Then we need to determine the sources of overhead in order to reduce this performance degradation due to the consolidation. And then we can study how the factors affecting this consolidation overhead affects or behaves. So in order to face these research challenges, our first contribution of this thesis is the THIS index, which is the consolidated index for CPU server saturation. The THIS index is calculated in a very simple manner. We can just do the product between these 2 ratios, which are the ratio of the performance degradation and the ratio of the energy consumption. All of these details of this formula are detailed in the documentation. So if you have any curiosity, you can ask me at the end. It's important to know that the THIS index can be applied in this case when the CPU utilization is around the saturation stadium. Also, the THIS index consider the number of consolidated servers that can be virtual machines or containers. So for a specific configuration of virtual machines and containers in a physical server, we have the value of the THIS index. Another interesting part of this index is that we have a reference diagonal, that is this diagonal I can point in here, in which we can divide the THIS area between the non-efficient consolidation from the efficient consolidation. That is, if I have a physical server and I have 4 virtual machines consolidated in these physical servers, I can represent the number of machines in this part of the graphic, and I can calculate the THIS value for this consolidation scenario. So if this value is under the diagonal, that is in the green part, I have an efficient consolidation. And if this value is on the red part of the graphic, I have an inefficient consolidation, in this case, considering the trade-off between the performance and the energy consumption. So we are looking for servers and consolidation configuration that this value are in the efficient consolidation area. Considering this, one of the most utilities of the THIS index is the benchmarking consolidation. This index allows a system administrator to distinguish the efficiency in a server consolidation degree. That is, if we have the graphic on the left side, we can see that if we have points in the green area, we can see more efficiency or less efficiency. So if a system administrator can distinguish these values, it can decide if a server is more efficient than another. In order to validate this index, we perform a set of experimentation based on the deterministic evaluation. In this case, we perform a huge set of experiments in order to take a lot of measurements using the monitorization and the benchmarking techniques. In this case, the measurements comes from a set of different physical servers and a set of different virtual machines or different containers that are allocated in these physical servers. Regarding the benchmarking workload, we use a CPU-intensive workload from two free benchmarks. In this case, are the SysBench and the StressIng. And the monitorization is done by software monitors and software and hardware monitors for the case of the power consumption. So it's important to know that all of this experimentation was done considering the real world. So we have a set of physical servers in which we vary the hypervisor type from the type 1, type 2, and container-based hypervisors. Also, we vary the benchmark kinds, configuring different parameters of the benchmark, and we vary the hardware features of these physical servers. So we have to consider a lot of facts in this real experimentation. In order to simplify all of these factors, we use the black box model in order to represent the physical system in which we submit the workload in the form of benchmark, and we are waiting and monitoring the system until the workload is completed. So we are not considering any queues or any queue system in this black box model. From the experimental setup, we vary all of the parameters I commented previously. We use all of these physical servers you can see in the table here with different number of CPUs and different RAM size memory. We vary also the hypervisors using the KVM, VirtualBox, and Docker containers. And also we use this hardware monitor for the power consumption. So let's move to the most interesting results from this dissertation. The first one is about the Thys index. In this picture here, you can see the representation of the Thys index considering the numbers of allocated machines, which can see virtual machines and containers. And we have these results for all of the set of physical servers. So we can see the division of these two areas using the green diagonal you can see here. So we can see in this graphic that the values of the Thys index behaves with a pattern. We can see that all of the Thys values starting increasing and then they start to decrease after an inflection point. This inflection point depends on the hardware features. And as a result, we can see that, for example, the RX server, which is the yellow one, has more efficient values of the Thys than the other servers. So with this graphic, we can compare the different physical servers. As I said previously, the inflection point depends on the server hardware features. And for example, the yellow function corresponds to the physical server with the best features. And this inflection point is under the diagonal, so it is the most efficient server considering this trade-off between the performance and the energy consumption. As I said, with this graphical representation, we can easily differ from the inefficient and efficient server consolidation configuration. So with the simple look, we can differ these servers and also the consolidations. For example, it's better to consolidate if we consider 4 virtual machines or 4 containers, it's better to have the blue server than the yellow server because the Thys index is more lower from the diagonal. On the other side, if we want to consider if we want to consolidate 7 virtual machines, the best option of physical server is the yellow one. Also, if we can look at the different benchmarks, we can see that if we vary the workload, if we vary the benchmark, the behavior of the FIS index is the same. We can this increase, and then after this inflection point, the FIS index going down. But we have different values, of course, depending on the benchmark. So this FIS index can be applied to any physical server, and it can be applied to any benchmark. After that, I would like to highlight the usefulness of this FIS index looking at this table. In this table, we can see the set of different physical servers sorted by the FIS index. This FIS index is calculated in this case, or considering the scalability vector size, which is the number of the maximum allocated virtual machines or containers the physical servers can support, and also the inflection point. So for a specific scenario, a system administrator can have this kind of table, and he or she can determine which physical server is better for this scenario particularly. In this case, the best physical server is the RX, and then we have the rest sorted by this FIS index. So on the one hand, we have the performance degradation. On the other hand, we have this power or energy savings, and we are trying to manage this trade-off between these two variables. So as I said previously, the FIS index depends on the physical server, the hypervisor, the benchmark. Definitely, the performance degradation determines the behavior of this FIS index. So the second contribution of this thesis, the server consolidation overhead, which determines this performance degradation. The overhead in this case is defined as the extra workload that the physical server has to perform in order to maintain all of this consolidation and also the hypervisor layers. So we identify the overhead of the virtualization, which is the red one, and the overhead of the consolidation of the virtual machines, which are accessing to the virtual resources, which are represented here by the green. Then in this thesis, we propose a general method in order to estimate the value of these two sources of overhead, and we can calculate the percentage of the useful work we are doing in any case. Here you can see the representation of the percentage of the useful work in the blue side, the overhead of the virtualization, which corresponds to the hypervisor in the red one, and the overhead of the consolidation, which corresponds to the green part. So in these two graphics, we can see that depending on the number of the consolidated virtual machines or containers, this percentage varies in any case. So we can see in this example here that a type 2 hypervisor has more consolidation due to the hypervisor than the type 1 hypervisor. So in any case, doing any combination, we can see that the consolidation is not for free, and the cost depends on the hypervisor implementation and the physical resources mainly. So I'm going to start to finish my presentation saying that we have one of these contributions is the FIS index and its graphical representation in order to determine the efficiency of a server considering this trade-off between performance and energy consumption. From the FIS index, we can compare different servers in any consolidation and virtualization scenario. Also, we determine the sources of this performance degradation in form of consolidation overhead, and we propose a general method in order to quantify and represent these overhead sources in order to manage in a more efficient manner these servers and data centers. And also, if you have curiosity, you can check out all of the public results, which are for indexed journals, different conference and workshops, one book chapter, posters, and some technical reports. So that's all from my side. And if you have any question, I'm very happy to answer it. Thank you for your time.